Thank you. So I'd like to thank the organizers for inviting me and giving me the opportunity to talk. Um, so the talk will based on some papers I wrote with many of them in the audience. Shai is not here, but I'm sure he knows everything I'm going to talk about. Uh, Very good. So I guess one of the motivation we had was ADS-CFT correspondence, which states that quantum gravity in ADS space supposed or conjectured to be equivalent to conformal on the conformal boundary of the ADS space. And make more precise physical observables, which we will consider here as scattering amplitudes. Sorry. Uh, oh, oh, oh. Sorry. uh, which one was the? Sorry, which one was the pointer? Is this the pointer? Oh, this one's the pointer. Sorry. And the physical observables, uh, which we will consider today, are on the quantum gravity side, are the scattering amplitudes. And again, it's conjectured to be equivalent to the correlation function in the dual conformal field CLA. A particular example we will study today, where on one side of duality, we have type 2B superstring CLA, called ADS5 cos S5, and the conformal field CLA, the conformal CLA is conjectured to be N4 super Yamils in 4 dimension. And the duality of sets between these two CLAs, in particular, say the coupling constant, which I use a complexified coupling constant in the gauge CLA, should be mapped to the coupling constant in string CLA, and both were called tau. The gauge CLA we will consider, because it's a gauge CLA, so there's a gauge group. And the gauge group we will consider today only focus on SU and gauge group. So the rank of the gauge group once again supposed to map to the parameter in the string CLA, and because this is a dimensionless parameter, so it's supposed to map to some dimensionless combination, which made out the length of the or radius of the ADS, and alpha pi. So in many talks, is the length square of the string. Okay, so this describes the mapping between the parameters, and just briefly remind you about the scattering amplitude in type 2B string theory. Well, we will really just discuss so-called low energy expansion or small alpha pi expansion of the scattering amplitudes. As you know, type 2B string theory is a closed string, so it describes the scattering of graviton at the leading order, namely when the string length is very small, you're supposed to reproduce, of course, Einstein-Hilbert term. Then when you study the effect of string, you start to get the collections. You can prove that because of maximal supersymmetry, the first field naive collection you might sort of should be there, actually not allowed because of maximal supersymmetry. And the first non-trivial collection starts from so-called R to the 4, so I should say R is Riemann tensor, R to the 4, namely you put a certain contraction about the what is remarkable is that this higher derivative collection turns out that you can completely fix using maximal supersymmetry as well as S-duality of type 2B string theory, in this case SO2Z. And as worked out by Michael and the collaborator, one can determine those coefficients or Wilson coefficients exactly for the first few orders. Here I only list two of them. And this coefficient turns out to be the non-holomorphic isosceles you saw already in many of the talks. I'm sure you know very well, but let me just say a little bit about the physics about the non-holomorphic isosceles. So you can do so-called Fourier mode decomposition, and the zero Fourier mode in the string theory language, they represent the string theory is a two-dimensional worksheet, and they represent the genus expansion. In the case, for example, the coefficient r to the 4, namely e3 half, you can work out this two represents, say, genus 0 and the genus 1 is the tallest contribution. Then the perturbation stops, essentially because of supersymmetry, but you receive, well, it's still receive infinite number of non-perturbative effects, so-called d incentons. Okay. So I guess our original plan was to try to rederive those superstring amplitudes from N4 super Yamu's. I like to call them sort of high precision ADSLT because now we're talking about the beyond the supergravity, and we'll talk about the beyond the perturbation because we will try to map, say, Yamu's incentons to D incenton. And core super Yamu's was famously known in 60s, 70s, has a so-called S duality, but well, S stands for strong weak, so it related the theory at the strong coupling to the weak coupling and study S duality. It's very difficult unless we know something about the exact property of this theory. That motivates, well, these two questions more or less related. That motivates a lot, try to understand the, say, correlation functions at non-perturbative level or study exact properties of the correlation function. Another motivation was kind of discussed by Shai. Some of the results you obtain can be think of as input or constraints for doing numeric or analytic bootstrap of N4 super Yamu's or equivalent type 2B superstring theory. So I will briefly remind you what physical quantity we would like to study, and I will introduce integrated correlator. Before I jump to say exact results or finite tau property of those objects, I'd like to mention a little bit about their property in perturbation. They are actually, even in perturbation, they are actually quite an interesting object. And as I emphasized, we'll have to study this object at the finite coupling tau. And to do that, we have to use sort of more advanced technique coming from supersymmetrical localization. So eventually, I will present some exact expressions. Especially, we like to emphasize the so-called lattice sun representation. At the end, I try to make a connection with the string amplitudes. Okay, so we like to study correlation function, or people call the superconformal primary operators. The name not important. In the fundamental field, they are just put a bunch of the scalar fields. So N4 super Yamu's because the supersymmetric theory, besides the gauge field, also has the scalars. And those scalars transform under the R symmetry, which turned out to be SO6. So this index I run from 1 to 6. It's much more convenient to get rid of this SO6 index by contracting this with some SO6 vector. And this vector has to be now just because we want traceless representation. The reason we want to traceless so that they are BPS operators. So those operators will be so-called BPS operator. This is often not emphasized, but well, it was introduced by intrigators as something called the U1 bonus symmetry. Those operators are neutral under this U1 bonus symmetry, which is important because only for such operator, the correlation function associated with this operator are SO to the invariant. Otherwise, suppose say something like a Cairo Lagrangian, which are not neutral, under the U1 bonus symmetry, the correlation function will not be SL to the invariant. Instead, they will be, say, SL to the covalent. Okay. In this talk, I will mostly focus on the simplest case where p equal to 2, because it's a SU and gauge U and CLA, so I cannot have only one phi. At least I need the two scalar fields. Just on very general ground, this was known long ago that say if you compute the 2 or 3 point function, it was already mentioned in some other talk, as a correlator is protected in the sense that they do not get any quantum collection. You can just compute them in free CLA. The first non-trivial case is the 4 points, where you have 4 insertion of operator, you want to compute them. We will separate out some piece called the free part, which, as I emphasized in the notation, is independent of the coupling tau. So this part you can compute, say, by weak contraction. And the remaining part is what we would like to study. As pointed out in this paper, for the remaining part, in fact, you can factorize into 2 pieces. And there's a prefactor I call the I4 here. Contains all the information about this Y dependence. Therefore, they know about all those SO6 property of this correlator. And then there's a single function, which magically independent on which SO6 channel you are looking at. And this is the object we would like to study, and in literature often called the reduced correlator. So like many conformal field CLA, the correlation function will be function of conformal cross ratios. I call U and V. And I emphasize it depends on the coupling. And of course, they would depend on the gauge group. We will study SU and gauge group. And for the SU and gauge group, this function is supposed to be so to the invariant. Okay. Very nice. So as I said, I like to the perturbation. So even in perturbation, the story is quite interesting already. In fact, as understood in series of these papers, that the perturbative integrand, in the sense that you don't do the loop integral, but just pure the integrand. So we have 4 insertion points. I call the x1, 2, and 3, 4. But then you also have the points which you want to integrate, say 5 until 4 plus L at the L loop. And the integrand, maybe I call the F here, as realized in those papers, that enjoy sort of enhanced permutation symmetry. So it turns out that you can treat those external insertion points, say 1, 2, 3, 4, as well as the integration point all together. They enjoy the complete permutation symmetry. And this enhanced permutation symmetry imposed a lot of constraint about the possible integrand. And in fact, in this series paper, they were able to construct the integrand, say, 10 loops. Here are sort of example they call the F graph by say writing integrand in terms of graph. So this is one loop integrand because I have 4 external points, one say loop point, that's one loop, and this will be 2 loops, this will be 3 loops. Once you get the integrand, of course, you have to do the integral and at 1 and 2 loops, the integral are rather simple. They are so-called ladders. But 3 loop take a lot of effort. In this paper, they did it, and I just copy a small piece of the answer from the paper. So I just want to emphasize how non-trivial it is. Okay, and surely I won't be able to do better than what they did. So rather, we would like to consider a simpler object. So instead of the correlation function itself, we will consider something called the integrated correlator introduced by Shai and his collaborators. I would just call them, say, the first integrated correlator, the second integrated correlator. And the definition is that you just take what I call the reduced correlator, which depend on the space-time or cross ratio, and you integrate over the cross ratio with a certain measure filed in Schweiz's paper. And you may notice the difference between the first and second integrate correlator. Well, the difference is measured, but the measure, I mean, the difference between these two measures is sort of minimal. It's just that for the second integrate correlator, you insert another object. They use the language of written type, and I copy the original notation. But if you are more familiar with the Feynman diagram, this is just sort of so-called a one-loop box integral. Okay. Those measure looks a bit, you may say, well, why it looks like this? It's well, for me, it's more convenient that instead of writing in this sort of polarized coordinate, rather you write in 4-dimension. Well, there's angle, so natural you try to write it in 4-dimension. And if we do that, especially combining this results F graph, this integrated correlator, what it really does for you is that instead of you just integrate out the loop point, you actually also integrate out all the external points in this F graph. And that's it. But of course, you cannot do that because this integral are conformal invariant. If you just really integrate all of them, they will be divergent. So you should model out the symmetry of those graph, namely the conformal symmetry. And such object actually studied by many people already, not here. So-called periods, I would like to call them periods of F graph because that's what we study. And once again, for the second integral correlator, it's basically the same thing, but now you just insert one more box integral. And people, especially Oliver Schnatz, developed special tools for evaluating those integrals. And if you do that, you will find that those, well, not this 3 example, actually, higher loops. You will find that those F graph contains multi-zetas, product of zetas, and so on and so forth. They may look rather complicated. But somehow, if you put those graphs together with the right coefficient, and all cancel out, and well, we actually know it will always cancel out because of supersymmetrical localization. So indeed, again, well, in these 2 papers by Shah and his cooperators, they point out that these 2 integrated correlators are related to the partition function of N2 star super Yamils. So they are related to N4 super Yamils by some mass deformation. And what you do is that take the partition function, you take, say, 4 derivative, then you set the mass to 0 because you want to go back to N4 super Yamils. Well, at least naively, it's not so surprising that taking 4 derivative, you're related to integrate the 4-point function because taking 4 derivative on the partition function, you bring down sort of 4 operators which are integrated. But of course, the details are much more complicated than what I said. But well, if we trust those papers, there's a precise relation between integrated correlators and the partition function in N2 star super Yamils. And the advantage of this connection is, of course, because of this famous work by Paston and as well as Nikusov, that the partition function of N2 star super Yamils can be computed exactly in the sense that rather than a path integral, the path integral localized in a finite dimensional integral. So for SU engaged theory, it's essentially just an n-dimensional integral. Just for the, if you're familiar with the story, in fact, even though it's a huge reduction from infinite dimensional integral to finite dimensional integral, nevertheless, this object, if we want to get some precise result for finite tau, it's not that easy. In particular, say you have to deal with the instanton contributions. This is coming from so-called the Nikusov partition function. Try to compute them, you have to list those Young tableaus and so on and so forth. So I guess it's fair to say it's not that easy. And furthermore, as I emphasized, the correlation function is supposed to be SL to Z invariant. It's not obvious, well, one can actually prove this is supposed to be SL to Z invariant, but it's not obvious the property of SL to Z invariant, namely what are the modular functions associated with those correlators, right? So, of course, we hope to do better. And without giving you any detail, we claim that for the first integrated correlator, and this n-dimensional integral, one can actually reduce to one-dimensional integral with a sort of lattice sum. And so, yeah, rather than justify this formula, but I will try to give you some consequence. So first of all, we notice that the coupling dependence combine into this little function we call the y and m, and it's very easy to prove that any of this combination, this function is manifestly SL to Z invariant. So we achieve that, and because of the coupling dependence all contained in here, so in some sense all the non-trivial information is contained in this little function I call the B and T here. And B and T is a rational function with a simple denominator. Denominator will be something like 1 plus T to 2n plus 1, and with a polynomial in the numerator. Okay. So rather give you expression for B and T, I will give you a generating function. I guess this is the goal in mathematics. So we have sort of counting problem because n represent the rank of the gauge group. So we have SU2 until say SUN. What you can do, you just sum over all the rank of gauge group, and then you obtain we would call the generating, the first integrated correlator. What we found is that the generating function associated B and T is given by this very simple formula. Well, there's a little branch cut, otherwise this is a very simple formula. So let's emphasize one more time what we are computing. What is the information this object contains? So this contains this 4-point correlation function for arbitrary n, and of course we integrate out the space-time dependence. But if we compare what I show you at the three loop, right? So that's only three loop. Therefore, I was not even able to discuss because it was so complicated. And although I won't be able to do it here, but we in fact was able to prove this formula by making a connection between the matrix model coming from localization and some other matrix or some other formula in literature called Zagi-Heller formula. Well, actually generalization of Zagi-Heller formula with the assumption of SL to Z. But of course, we know the correlator is supposed to be SL to Z invariant. Okay. So as I said, so rather than really proving this formula, I will just discuss some sequence of this formula. So let me say a few words. So first of all, this formula, in fact, immediately implies that if you do a spectrum decomposition, integrated correlator, I guess for experts, you immediately see that there's no mass cast performance, well, as pointed out in this paper. And if you stare on generating function a bit, you may notice that it actually obeys some differential equation. In particular, take a 2 derivative with respect to t and the 2 derivative with respect to z. It will obey some equation. And 2 derivative with respect to z clearly can be translated into, say, difference for Cn. And derivative with respect to t by integration by part, this can be translated into difference on tau. Put everything together, we found that the integrated correlator itself, rather than the generating function, very simple. We call the Laplace difference equation. As you can see, this is essentially a recursion formula. Once you give me the integrated correlator for SU2, namely C2, because C1 is 0. There's no SU1, right? And in fact, this formula is very efficient to generate the Cn as you wish once I give you a C2. And furthermore, the generating function, well, of course, once you have generating function, you can write a small counter integral to the integrated correlator around the z equal to 0. But now then you can deform the contour. As you notice, the generating function has some simple cuts. And it actually can streamline the larger n expansion of the integrated correlator, especially at the finite tau, which sometimes is a bit tricky to do it. So, okay, before I discuss the larger n expansion at the finite tau, let me just discuss a little bit more traditional, say, the whole genus expansion. And in this expansion, you take an n large, you kind of keep the whole coupling, which is n g Hamilton square, fixed. And turns out in any genus, this first integrated correlator always take this form. You probably already saw such a formula before. And here I just gave you how this, say, integrand looks like at the genus 0. Well, I write it as a hypergeometric function. So you can also write it in terms of the Bessel function, like J1 square minus J2 square. And from this little integral formula, you can, of course, do small lambda expansion. You can also do large lambda expansion. So I mentioned that in the perturbation, the correlation function can also be described by periods of F graph. And indeed, we compare this formula with the periods of F graph up to 4 loops. But given that localization gives you the result to any loop orders, in fact, this if you use it carefully or cleverly by combining with some other techniques, actually it allows you to predict loop integrals at the higher loops, and those loop integrals, as far as I know, cannot be computed by any other means. Then, of course, by making connection with ADS-LT, you would also like to do large lambda expansion. And famously, and for superyamuos, in the strong coupling of 1 over lambda expansion are not Bohr-sumable. I guess this asymptotic theory is so simple. We can even say compute using the standard resurgence to find out all the exponential decay terms analytically, basically to any order we want. And so this is just genus 0, and the structure almost the same for genus 1, and so on and so forth. But for the purpose of this talk, as I said, we want to consider SL2Z property. So we like to study larger n expansion, but with fixed tau. In literature, this is often called a very strong coupling limit, because the whole lambda, the so-called lambda, now it became very, very, it goes as n. In this limit, according to, if you still remember, according to ADS-LT dictionary, the 1 over n expansion became a small alpha pi expansion. So from this little contour integral I mentioned earlier, we obtained the integrated correlator in the larger expansion with fixed tau. And here's the structure. So you have leading order, which is independent of the coupling. Or said another way, in the string theory language, this is the leading order in alpha pi. And of course, they represent the supergravity contribution. Then you have all the lower order collections in 1 over n, or 1 over square root of n, again, translated into alpha pi. So it gives the string collections. And indeed, you see exactly the first term will be E3 half, then you see E5 half that appears in the result by Michael and his collaborator. And besides those, say, sort of perturbative terms in 1 over n, we also have non-perturbative terms, namely the term which exponentially decay in the large range limit. Um, so this object more or less like a so-called non-holomorphic Einstein series, but attached with this exponential factor. Um, and if we translate it into string theory, um, so square root of m became 1 over alpha pi. So this combination precisely is the tension of the PQ string. So this term essentially we would like to interpret as the Wirth PQ string. And in the language of resurgence, it just says that this power theory in 1 over n with fixed tau are asymptotic, and you need at exponentially decay to make this asymptotic theory well defined. I think it was shown by Daniel and his student. I believe Rodolfo gave a talk here. That's indeed the case. They kind of reproduce this using exactly resurgence. Of course, do a slightly simple resurgence. Instead of doing this in the SL to Z invariant fashion, once you have SL to Z result, of course, you can go back to Holt. And if you do that, you will find this D function behave like, in the Holt limit, behave like exponentially square root of lambda. And the Einstein series, or the power series, behave like 1 over square root of lambda. And these two terms, of course, as shown by many people, are related by indeed resurgence. And this is much simpler resurgence, which in fact, I also mentioned earlier. So in the remaining time, I will discuss, well, sorry, I will say a bit more about the first inequality. And for those who maybe, bored with the fact that we didn't discuss the kinematics. We integrate out all the, space-time dependence. You may complain you want the space-time dependence. And in fact, from the integrated correlator, which has no space-time dependence, you sort of can use, people would like call an electric bootstrap to reconstruct the space-time dependence by, say, knowing a little bit about the structure of the space-time dependence. Essentially, in some sense, that you write the ansatz, and the integrated correlator gave you constraints on those ansatz. For the first few order, well, the first integrated correlator and the second integrated correlator allows you to completely fix the function to this order. And let me remind you, the flat space result by Michael and his collaborator, you may be familiar, this term is precisely so-called supergravity amplitude, which is supposed to relate it to R, and this is the term gives you R to the 4 because I divided by R to the 4 on this side, and this term, it gives you D4 R to the 4 because S squared, the Mandelstam variable goes like, 4 derivative. So S goes to 2 derivative, S squared goes to 4 derivative. Okay. Very good. So I will then discuss second integral correlator. And this is much more complicated. First of all, you already see the complication in planar limit. Besides the term which very much like the first integral correlator, now we get a sort of double the complication. So we have two-dimensional integral instead of one-dimensional integral. Again, you got a sort of Bessel functions, but now you have 4 Bessels instead of 2. And furthermore, these 4 Bessel functions are coupled, right, because of this denominator. Okay. Shai and Pufu, they analyze this for the planar limit, and later in our paper, we generalize it to, say, beyond the planar, so on and so forth. But once again, I like to discuss the expansion, but with fixed tau. Okay. So in this case, we can naturally separate this say large range expansion into a few pieces. Well, the first piece is just constant, kind of simple, and indeed they're important objects because they represent, say, tree-level supergravity contribution. Then you have tau dependence, and unlike in the first integral correlator, now this tau dependence we separate into 2 pieces, and the first part we call the H half, namely because they expand in terms of, say, in the one n expansion, they depend on n like a square root of n. Okay, and the second piece, which I call the hi here, because as n dependence, they will in the say integer power n. And for each half, turns out, although the computing it is not easy, but turns out that the answer looks rather simple. Once again, they are given by non-holomorphic Einstein series, very similar to the first integral correlator, if you remember. And in fact, we can determine this this H half completely because they obey Laplace, pseudo-Laplace difference equation. Of course, it's not difference anymore because I'm talking about the Lagrange expansion. So this equation should be understood as a Lagrange expansion. And this was conjectured, but nevertheless, they checked this formula extensively. But if you do believe this equation, then this equation essentially determined this H half integer terms completely once you give me the initial data, we knew the initial data. Okay, and you notice this was like difference equation, but with sort of sourced and sourced by the first integrated correlator. Okay, I will focus more on so-called integer power in 101 expansion. Well, first of all, there's a sort of the coupling independent terms, and the holographic interpretation of those coupling independent terms are the supergravity, because supergravity does not depend on tau. And they are like, instead of tree level, now they are like one loop, maybe two loop contributions, and so on and so forth. Let me not discuss those terms. They are very interesting objects, but let me not discuss them for this talk. And for the coupling dependent terms, they are given by what is called the generalized Einstein series. Well, the general formula of, unlike Einstein series, the general for generalized Einstein series is not known, but that in some sense they're defined by this inhomogeneous Laplace equation and provide sort of boundary condition. Presumably there's a unique solution, and you kind of can see this is a much more complicated object compared to Einstein series. So in particular, say from physics terminology, they contain the so-called instanton and the anti-instanton pairs due to this Soston. Anyways, so this is a much more complicated object, but they're supposed to appear. We kind of knew it because, as already again by Michael and his collaborator, we should see it because for the first few the alpha prior collection, at least earlier, there's one more order I could have listed, namely D6 out to the 4, and it was new worked out by in those papers that the Wilson coefficient for D6 out of 4 is precisely given by this probably the generalized Einstein series. And so we're supposed to get it, and indeed we got it. But for this integrated correlator, we of course can compute much more. We went now like 101 to the 7, but here I just list a few of them. What is important about this generalized Einstein series is about the cost performance. As I said, I guess the general solution is not known, but due to the work by King and her collaborator, I think generally one can write this solution in sort of in two pieces. One I would call a particular solution. I even won't give you the formula, but roughly speaking, it's like a product of base LKs, K0, K1, maybe with just with some polynomials. And one important point is that they don't contain cost performance. But then you have a homogeneous solution to that equation you have to add. And this homogeneous solution turns out to contain, in general, contains cost performance contributions, especially when S equal to 6 or bigger. And that's already relevant at 1n to the q. Okay? But what is remarkable about this integrated correlator is that, well, I guess kind of expecting this from localization. Anyway, there are no cusp forms. Yeah, the Holm cusp forms. That's why. Yeah, that's why. That's why. Yeah. So, but they somehow magically cancel, and well, I'm sure these two things are probably not related, but just to remind you, in perturbation, there's also a sort of cancellation for the multicitas. So here's an example of the cancellation. So this was already computed in some earlier paper. Uh, well, we computed those coefficients from localization. The coefficient looks a bit random. We didn't notice, whatever property this coefficient has. But now, due to King's work, we understood in some sense that the coefficient, these three coefficients in some sense are not completely independent. They have to coincide such that this cusp forms cancel out. And this cancellation happens as we check the 1 to the 7, and certainly we can probably do better than that. But this cancellation of cusp forms also suggests you that this generalized Ising series are probably not the best basis for describing the integrated correlator. So we introduce sort of new modular basis. We use a very similar notation, uh, but I guess the main point is that unlike the generalized Ising series, which has a cusp form, namely S started from 6, this we introduce can be written as again lattice sun. So you probably already remember that was a sort of lattice sun representation for the first integer correlator. In that case, it was for finite n, arbitrary n, but now I'm talking about the only large n. So, we would really like to understand the finite n story, but anyway, let's focus on large n for the moment. And instead of say sort of one lattice sun, now we have to sum over two lattice momenta. The third one is constrained. And instead of it was one-dimensional T integral, now it's actually much more complicated. It's a three-dimensional integral. And the integrand, which again independent on the coupling tau, tau always appear in the exponent only, I guess in math literature called. So tau is only contained here, and in some sense, all the non-trivial information is contained in this function I call it B again. This is a symmetrical function of T1, T2, T3, and has a square root. So unlike in the first integral correlator case, which was a rational function, and although it's not trivial, but it was worked out by Zagier. There's a systematic way to construct this object. So I will not discuss it, but we know how to construct it for basically all the relevant IJW. And what I really just want to mention is that this base sort of differential equation act on T1, T2, T3. And once again, so this differential equation, you can do an integration by part, translate it into differential equation for this function, pick out some boundary terms, and the boundary term will give you sort of source. Sorry, well, I didn't write the differential equations, but anyway, so that term will give you some source. That source will be like Ising series times another Ising series, or linear Ising series. Using that differential equation, we understand that this new object we introduce is essentially linear combination of the original generalized Ising series with a particular coefficient, as well as some Ising series you can of course remove, say by hand even. And the statement is that this linear combination, almost by construction, is, I don't know if that's a mathematical theorem, but given the fact this is can be written as a lattice sun, this linear combination turns out always free of the cusp forms. And we would claim that at least in the large n expansion, this will form the right basis for the integrated correlator. And as I said, we did this until 1 to the 7, which are highly non-trivial computation because, again, you have to compute the instantons and so on and so forth. Oh, I messed up the, okay, yeah. I forgot the clock, it was 5 minutes early. But anyway, so let me summarize what I did. So, roughly speaking, I discussed what I call the first and the second integrated correlators. And in the connection with the localization, just to remind you, so the first integrated correlator is basically two mass derivative of the N2 star partition function, then you set the mass to 0. And the second integrated correlator is a four mass derivative. Okay? And we more or less know everything about the first integrated correlator for arbitrary n and arbitrary tau. And as I said, we even have a generating function which represents all the n dependence. And for the second integrated correlator, we know, for finite n, we know much less. We basically know nothing. Well, we know a little bit, but we know very little. So we focus on larger n expansion, but once again, because we want to study modularity, so larger n fixed tau. And for this integrated second integrated correlator, larger n expansion naturally separated into two pieces, and one piece is expansion in 1n, but with a half integer. This object, although we don't have proof, but there's a lot of strong evidence. We found this part actually very much similar to the first integrated correlator because they're given by, again, non-holomorphic Einstein series, just with some change of the coefficient. And we know exactly what are the coefficients because they obey sort of recursion relation. But then for the integer part, in our very first paper with Shai and others, we thought that we should represent in terms of generalized Einstein series, which kind of natural because Michael and his collaborators saw the generalized Einstein series in the 6004. Of course, naturally, we try to write it in terms of generalized Einstein series. Then, again, due to the work by King and her collaborator, it was understood that the generalized Einstein series has a Casper forms, but we don't expect Casper forms from this localization formula. So they have to cancel, and indeed, we check especially they do cancel, and because of this cancellation of Casper forms, we realize, in fact, it's better use some other modular invariant functions which are manifest of a cancellation of this Casper forms. I discussed a little bit about the connection with the string amplitude in the larger n expansion fixed tau. They are related to the small alpha pi expansion of the string amplitude with a fixed string. We saw all those modular functions, say, if I half, as well as the generalized Einstein series, which also appears in string theory, appears in our integrated correlator. As I emphasized, in fact, by combining some other technique, you can even do better to reconstruct the space-time dependence, namely the say UV cross ratio dependence, which match exactly the, say, in the so-called million space, match exactly the string amplitudes in, when you take a flat space limit, match with the string amplitude in 10 dimension. There are, of course, a lot of things we can discuss further. In particular, as I already probably emphasized several times, that it would be interesting to study the second integrated, of course, finite n, at the same level of what we did for the first integrated correlator. But there may be something simpler one can do. For example, we have this asymptotic theory already in the preliminary. Well, I guess for no reason, we should not work out the resurgence, especially given this conference. I only discussed SU and gauge group. One can, of course, study some other gauge groups, like we did a little bit already, then you did it for exceptional as well. And for the modularity point of view. Some other gauge group are in some sense more interesting because they are not modular invariant. In fact, they will exchange the gauge groups. And as I said, indeed, for the first integral correlator, there was already some work, but of course, there was no work for the second integral correlator. One can also consider, instead of those simplest four-point function, you can consider more general four-point function. As I like the very first slide, I introduced this chiral primary operator, superconformal primary operator for arbitrary dimension. I focus on the lowest dimension because you can start to think, say, more general four-point function and study, well, at least say integrate version of those four-point function. One particularly interesting correlator, well, one particular type of interesting correlator would be so-called in literature called light or heavy light correlator, where light means this two operator has very lowest dimension, but you could consider the four-point function with two light operator and two heavy operator. And if the heavy operator is so heavy, in particular, say, like behave like n squared or heavier, this will change the geometry of ADS5 cross S5, so allows you to start this object from the geometric point of view, and which it would be interesting, to see the connection from field theory. Besides the local operator, you can of course consider, non-local object like defects. It has already some work by considering Wilson loop. That's one typical defect one can consider in and for super Yamir's. And in particular, if we like to study, say, modular properties of this object, as you know, Wilson loop is not a modular invariant, so it will relate to, say, for example, under inversion, it will relate to the Holt loop. It would be very interesting to understand the associated, say, modular forms of this object. So let me finish this little picture. And due to the time constraint, so I didn't really discuss much detail, but I guess punchline, well, some people like to call enforceable Yamir's as the simplest quantum field theory, I guess with good reasons. You can view this integrated correlators, ones which I discussed or ones I mentioned only in my previous slide, as a sort of, say, the simplest observable in the simplest quantum field theory. Indeed, so unlike people from scattering amplitude like myself, unlike the scattering amplitude which has an infrared divergence and you cannot compute much, this object is infrared finite, UV finite. You can even compute at finite tau. Even though I call it the simplest observable, but at least I probably touched some of the topics. As you can see, this is related to many interesting other topics in some in a very non-trivial way. So thank you very much. That's right. So Tulip, in that case, I don't know. Do they do they get like beyond the? Yeah. Yeah. Right. So the object is you are referring to the object they call the AIJ. Is that what you think? Yeah. Yeah. So I should give the reference. So this object is basically the AIJ. Uh, well, um, um, I guess some of them appear, some of them they don't appear. I believe they didn't get very far. I don't know. Michael can correct me. I think we have many more turns. So I mean, for integral quality, we basically have infinite number of such objects. Yeah. So it's exactly the same object. I don't know. Yeah. So so which I call W here. Non-solution. Oh, sorry. Oh, yeah. So it's not really virtual instanton, I would say. Uh, Maybe settle point uh, because um, you know because of this the prefactor I, right? So I would say it's a settle points rather than say instanton. Yeah, I guess well, we don't really any computer from string theory side, but as you can see, there's an I, right? It's not the, I wouldn't say it's a instanton. Uh, yeah, but not, as you said, that's not as stable. Yeah, 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 yeah. Yeah. Uh, Not really. So this was fixed uh, by localization computation. So in the sense that, say we write the basis, we kind of know what are the bases supposed to be there. We put the localization data, then fix those coefficients. And yeah, as I said, only later we notice actually the Kasparov cancel out. But I guess one reason I can provide is that the building is a lattice representation, uh, like a modular graph. But yeah, thanks.